In level 3, we will be using some formulas called the half angle and double angle identities, and simplifying more trig expressions and verifying some trig equations or trig identities. So to start off, we are going to use the half angle identities for these first two examples. These are the half angle identities. And the way they work, if I want to find the exact value of sine of negative 22.5, and negative 22.5 happens to be half of an angle that's on the unit circle. It's half of 45 degrees. So this is the same as sine of 45, well, negative 45 divided by 2. And so the way the half angle identity works is if I can rewrite an angle as some angle on the unit circle divided by 2, then I can use this half angle identity. So I'm going to use this top one, sine of a over 2. So my a in this case is going to be negative 45 degrees. So a divided by 2 is equivalent to negative 22.5. And what I'm going to do is just plug in to the other side of the equation. So I get plus or minus the square root of 1 minus cosine of negative 45 degrees divided by 2. And then I evaluate cosine of negative 45 degrees. And cosine of negative 45 degrees is radical 2 over 2. So I get plus or minus the square root of 1 minus radical 2 over 2 divided by 2. And for our purposes, I'm going to be okay with you leaving your answer just like that. It can be simplified more, but for now, it's okay to just leave it like that as long as you plug in correctly and evaluate correctly. In the next example, it's in radians now, but we still want to think of an angle that pi over 12 is half of some angle on the unit circle. So pi over 12 happens to be half of pi over 6. So if I make my a pi over 6, pi over 6 divided by 2 does give me pi over 12. So a is pi over 6. And then I just plug into that formula. So cosine of a over 2 is plus or minus the square root of 1 plus cosine of a, or cosine of pi over 6, divided by 2. And I evaluate cosine of pi over 6. Cosine of pi over 6 is radical 3 over 2, so I get plus or minus the square root of 1 plus radical 3 over 2 divided by 2. And again, you can just leave your answer like that. No need to simplify any more than that. In these next examples, we're going to be using the double angle identities, which are in this box right here. And again, you don't have to memorize these. We want to find the exact value of sine of 2 theta given cosine theta equals 3/5, and theta is between 0 and pi over 2. So we need to draw a triangle for this one in the coordinate plane. Theta is between 0 and pi over 2, so that's in quadrant 1. And cosine theta is 3/5. That means, remember, this is x over r. So the x coordinate is 3, the radius is 5, and using Pythagorean theorem, this is a Pythagorean triple, you get 4 for your y coordinate. And now we want to find sine of 2 theta using this formula up here. It's 2 sine theta cosine theta. So sine of 2 theta is going to be 2, and then sine of theta in this triangle is going to be, well, y over r, 4 over 5. Cosine of theta in this triangle is 3 over 5. And we just simplify. This gives us 24 over 5. Or 25, sorry. 24 over 25. The next one's similar. Now we're evaluating cosine of 2 theta given tangent theta equals 1/2 and theta is between pi and 3 pi over 2. That is going to be in quadrant 3. Tangent theta is 1/2. This is y over x, so the y would be 1, the x 2, and they're both negative because we're in quadrant 3. And now to evaluate cosine of 2 theta, we can pick any of these 3, whichever one seems the most fun. I'll use the top one. Cosine squared theta minus sine squared theta. So cosine squared theta, well, cosine of theta in this triangle, I need to do the Pythagorean theorem to find the r, and you should get radical 5. So cosine is x over r, and that's going to be squared. So we get negative 2 over radical 5 squared minus, and then for sine squared theta, sine of theta in this triangle, y over r, is negative 1 over radical 5, and it's going to be squared. And then that comes out to, when I square that first fraction, negative 2 over 5 squared is 4/5. And then negative 1 over radical 5 squared is positive 1/5. So 4/5 minus 1/5 is 3/5. The next part of level 3 is verifying identities. You get an identity or an equation that you're told is true, and you have to show that it's true. So you have to prove that it works out. So it's kind of nice because you already know what your answer is. You just have to make sure you can get there. So I want to take tangent theta over secant theta and simplify it so I end up with just sine theta. I'm just verifying that it works. So I rewrite tangent theta as sine theta over cosine theta. Secant theta is 1 over cosine theta. My cosine thetas cancel, and we get sine theta over 1, or just sine theta. So it worked. We did it. In the next example, I'm first going to recognize one of my Pythagorean identities. Secant squared theta minus 1 equals tangent squared theta. So I can replace secant squared theta minus 1 with tangent squared theta. I get cotangent theta times tangent squared theta. And we're trying to show that this equals tangent theta. So I'm going to simplify this. Well, first I'm going to write cotangent theta as cosine theta over sine theta. Tangent squared theta is sine squared theta over cosine squared theta. And this cosine cancels with one of these, so I'm just going to cross off the square. This sine theta cancels with one of the sines, and we end up with sine theta over cosine theta, which is tangent theta. So we did it. In this next example, when we have fractions, we need common denominators to combine them into a single fraction. So secant theta over sine theta needs to be multiplied by cosine theta over cosine theta. And we'll get sine theta cosine theta as the denominator. And then sine theta over cosine theta I'm going to multiply by sine theta over sine theta. So for my first fraction, when I multiply secant theta times cosine theta, since those are reciprocals, I just get 1 over sine theta cosine theta. And for the second fraction, we get sine theta times sine theta, or sine squared theta, over sine theta cosine theta. Since we have common denominators, I can combine these into one fraction, 1 minus sine squared theta over sine theta cosine theta. And 1 minus sine squared theta just so happens to be one of our Pythagorean identities. Looking up here, 1 minus sine squared theta is cosine squared theta over sine theta cosine theta. And I can cancel the cosine theta on the bottom with one of the cosine thetas on the top. We get cosine theta over sine theta, which is cotangent theta. And we did it. That's what we were hoping for. And for the last example, let's rewrite tangent theta and cotangent theta. So we get 1 plus sine theta over cosine theta, and 1 plus cosine theta over sine theta. Now I want to combine that 1 with the sine theta over cosine theta, so I could rewrite the 1 as cosine theta over cosine theta, so I get common denominators. That's the same as 1. And I can do the same thing on the bottom. I could rewrite that 1 as sine theta over sine theta. Again, so I have common denominators. Then I can add together my expressions, so I can add these together now that they have common denominators, and we get cosine theta plus sine theta over cosine theta divided by, and then adding the bottoms together, we get sine theta plus cosine theta over sine theta. And since we have cosine theta plus sine theta, which is equivalent to sine theta plus cosine theta, those expressions cancel. And we are left with 1 over cosine theta divided by 1 over sine theta. And this is the same as sine theta over cosine theta, which equals tangent theta. And we're done. We got what we were looking for. We verified the identity.